The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Clearly, I'm not Rusty Owens, so I'm going to just do the best I can to just show slides and run through some of these because I don't want you to lose that opportunity to see what he had. So there's a lot of discussions about the actual project. So he's going to talk about it's a design build project, and it's the Christopher Bond Bridge in Missouri. So basically, it had a lot of requirements like safety, mobility, capacity was the main thing that was coming to a challenge. So this is about 66 years old. It was originally built in 1952. So you can see some of the information about it's in downtown Kansas City. It spans 2 counties, about 100,000 vehicles a day. So this is the budget. And this is some more details about the budget. So the design build project, and some of the main focus was that it was going to be a fast construction. They want a fixed cost, best value, flexibility, and innovation. Again, some more information about the project, the budget. It's a landmark bridge. They improve safety, mobility, aesthetics, and capacity. And so these are the way they were scoring it, and they had about 20 points for aesthetics, as you can see. So they recommended the best value proposal. So this was a decision made in 2007, and this was completed in 2010, as you can see. Some more pictures. This is the project team: Missouri DOT, HNTB, and Geiger was a ready-mix supplier. So this is a joint venture between all the parties. So that when you have a JV, that's a shared risk. So you try to utilize expertise in all stakeholders in the construction, and essentially you're sharing their expertise in terms of personnel, equipment, and as well as resources. So basically, you have to, whenever you have the JV process, you're building the cultures of the different companies, so there always can be challenges. So you want to make sure in terms of quality, everything goes right. There are third-party approvals to deal with. Okay, so this is the original prescription specification for Missouri DOT. They had a standard class of concrete, and this is very similar to a lot of DOTs. So they have prescriptive minimums and maximums of different, cements and so on. The performance criteria was basically a 75-year design life, which was actually beyond the Missouri DOT spec scope for design requirements. So essentially the performance testing had laboratory as well as field testing. So this was a design requirements for the Missouri DOT. As you can see, different class of concrete, the strength requirements are listed. So you also have maximum slump requirements, and there is how much water cement ratio, whether it's air and train or non-air and train. Again, this seems like a very similar to a table from the ACI 211 guide. So this is very standard in a lot of DOTs, which will have, they tie the strength with the water cement ratio requirement. And they also other things like you can use SCMs up to a maximum of 40%. You can use a C or an F up to a maximum of 25%. If it's a slag, up to a maximum of 30%. And they allowed silica fume as well in certain applications. So the performance requirements for this project was that Parsons in Chicago was doing the work. The strength requirement for the pylon was 7,000, and for the bridge deck was 8,000. The water cement ratio was done by the AASHTO T318, so Cass, you can be happy. So they were testing by the microwave test, so they did have that acceptance requirements. And they were doing the Coulomb test as well, ASTM C1202. And they had some more requirements like the ASTM-C 666 test, that's for freezing and thawing, and as well as the salt scaling resistance, the ASTM 6672. So they had all these requirements. Building the bridge, so there's going to be a lot of pictures. I'm going to show you real quickly. So this is just a typical DOT project. Lowering the permanent casing into the temporary casing. Again, setting the permanent casings for the drill shafts in the riverbed. Final alignment. So okay, this is a drill shaft mix design. So this was their typical Missouri DOT spec, prescriptive spec. As you can see, this would have a total of 705 pounds cementitious, a class B2 concrete. Depending on the class of sand, you got to put 705 pounds of cementitious. So what they were able to do with the performance spec is to go to about a 450, 150. So that's about 105 pounds less cementitious. And also they were using obviously a hydration stabilizer, 0.40 water cement ratio, 4,028 days, pretty flowing concrete, air entrained. So the big benefit obviously was 105 pounds reduced cementitious. So that's a big, can help you in reducing cracking and the temperature at high temperature as well. So that was the real shaft mix design. So it just shows you an example of about 2,000 cubic yards of concrete in a single day for the Cofferdam seal. More pictures, ready mix concrete trucks from above. Concrete being placed in the hopper. You can see the hopper. And from below is pumped from the shore. So this is a seal mix design. The seal mix design was supposed to have about 660 pounds of total cementitious and 0.45 water cement ratio maximum, 4,028 days, 6-inch slump, 5% minimum air entrained. And they also, Parsons required a low heat of hydration mix design, meeting ASTM-C 150 of 70 calories per gram. So primarily to control the temperature related cracking issues. So the performance spec ended up having about 610 pounds total, and they were using more fly ash, as you can see, about 40% fly ash in the mixture. And they had again, it was air entrained, 0.42, the strength was a little higher, and they were able to achieve the 58 calories per gram, so it's below the requirement here. So they were able to satisfy that, so they were able to achieve that with 50 pounds less cementitious in the concrete. So obviously that helped a lot, reducing it from 495 to 366. That really helped reduce the temperature substantially. Picture of a dry cofferdam, casings removed. So they had about 235 miles of rebar work, so it just sees you the scope of the amount of work involved. That's a 3D shop drawing of the integrated, like all the rebar cages and everything. So again, some more pictures of rebar cages in the first concrete lift. This is the pylon structure. And again, the pylon mix design had about 790 pounds. That would be the Missouri DOT prescription, 3/4 inch aggregate with the sand, and then 4,028 days. Again, this would be their 6-inch lump, 5% minimum air entrainment. If you remember correctly, originally they wanted 7,028 days for the pylon mix. So, but this is the typical pylon mix. So what they ended up, this particular case, they ended up having about, looks like about 740 pounds total instead of 790 pounds cementitious. So a little bit lower, and because they had to get the 7,000 psi instead of the usual 4,000. And they were able to get that with a fly ash slag cement blend. It was air entrained, 8-inch slump concrete, and there was an aggregate blending between the 3/4 and 3/8 inch here, and they were getting about 50 pounds less cementitious as well. So some benefits here in the pylon mix design. Again, pacing concrete for second lift, downstrong pylon leg, constructing the roadway strut. Again, just shows you the complicated rebar assembly here. Two cranes moving the floor beam from the truck to the barge. That's the deck beam being placed. Shock fin girder. This shows you the different, what we talked about, the pylon leg, the floor beam, the edge girder. The pier table from 2009. This This is a view from the river channel, again from 2009. So from the top, 314 feet from the river. And so here's the bridge deck mix design. So the usually I guess in this particular case, the 8,000 psi bridge deck was a requirement. So there was no prescriptive requirement here, if you remember, because this was an 8,000 psi requirement. But they wanted air entrainment. They wanted an aggregate durability of 95% higher than C666. Permeability below 2,000 coulombs per C1202. Scaling rating of 0 to 2 per C672. And the general contractor required 75% of the strength in 2 to 3 days, basically 40 to 72 hours of construction scheduling. And once again, they were verifying the water cement ratio in the job site with the AASHTO T318. So what they ended up doing in this particular case is they used a cement, a glass of ash, and a small amount of silica fume. So if you see here, this is about 585, about 705 pounds total, so about 5% silica fume. So they used a 3/4 inch 3/8, again a sand, and they were get about 0.34 water cement ratio with 8,000. They were able to attain very easily at 28 days. Again, these are some of the and again they were able to meet all the other requirements. You can see performance requirements here. Again, all the mix design was allowed. There was no actual prescriptive suggested mix design in this case. Some more pictures of the bridge deck and framing plan, precast deck panel, the final stay cable installed. So the paving mix design, so in this case the original Missouri DOT spec had 420 pound cement with a Class C ash at 140 pounds. So that's about 560 total. And it was air entrained mix with a high range, small amount of high range. In this particular case, the producer went to a 390, 130, so that's about 40 pounds less cementitious in the mix, 520 pounds total for a paving concrete. And they were able to do it with a 0.40 water cement ratio, which is pretty good, about 216 pounds of water in the mix. They had a 3/4 inch, 3/8 inch aggregate, water reducer about 9 ounces a yard. So again, perhaps if they had probably gone to an even higher aggregate size, they could even pull some more cementitious out. Just gives you an idea that what you could do if you're not curtailed by this prescriptive spec. You have to put 560 pounds of cementitious. There's a lot of freedom. Producers can optimize the mixtures, reducing the cementitious, using different SEMs, for example, to get the performance. Just gives you an idea of the another picture here, the Armour Road 2010, different projects. So sorry, I didn't even realize about this presentation. This presentation was developed by Rusty. He could not be here. I just saw these slides about an hour ago. So I tried to do the best I could. But if you can see the idea that throughout, for all mixed designs, they were able to reduce the cementitious substantially, right? And they were able to use most of the time a higher amount of SEMs than what the original Missouri DOT spec allowed. So they were obviously making a lot more greener concrete. There were not much cracking type studies done, but they had other performances like the coulombs, freezing and thawing, scaling resistance. So there were a lot of performance testing being done. So this gives you an example of what some of the innovation that can happen if it's allowed, if the producers and contractors are allowed if you just give them the performance that you want to target and just allow them to do the freedom to do what they want to do. So it is possible that some things can be done. So I'll conclude this talk.
Karthik, can you comment? I know this, you not know the details of the project, but just an interesting question. That project, it looked like from some of the mixes that were used for the same project, they were in some cases using Class C ash, in other cases using Class F, and it didn't appear to be related to
any performance
ability to,
any performance requirements as such.
What would be the reasons on a project to mix the use of ashes?
I guess I've not had a chance to talk to Rusty at all about this. My guess would have been purely an availability issue. That would be the reason. probably just an availability issue. That would be my guess. Yeah.
I guess as long as we're at this, you know, Kaz talked about going to a larger course aggregate size, minimizing base volume as a way to help control shrinkage. On these projects, it looked like 3/4 inch aggregate was used. Other than the fact that if you have, like they had pretty heavy reinforcement, you probably weren't going to be able to get too large an aggregate in that, but there were, it looked like some applications there that they could have gone to larger aggregate sizes. You want to comment on that?
Yes, I think when I look at this, particularly for the paving concrete, definitely they could have done more than 3/4 inch. Some of the other bridge deck concrete, pylon and all, I can see this a complicated rebar arrangement. There's no way to get an 1.5 inch even there probably. But the paving concrete, they could have done more, definitely. But even if you think about it, even with the 3/4 inch, they were able to get it down to 520 pounds total cementitious for a paving concrete, which is pretty good. If you compare with a lot of mixes around the country, they're mostly at 560, 580 pounds total. So that's still a big step forward. But perhaps they can drive it down to below 500 pounds if they go to 2-inch size for paving concrete. Thank you.